Light travels at a fixed speed, 300,000 kilometers per second. When you point a telescope at a distant object and measure its brightness, you're measuring photons that left that surface hours or days ago, carrying information encoded in wavelengths that don't lie. Spectroscopy reveals composition. Thermal imaging reveals temperature. Photometry reveals reflected light. These aren't opinions or interpretations, they're measurements, hard data, the kind of evidence that builds careers and fills textbooks because it represents observable, repeatable truth. On April 12, 2025, Dr. Sarah sat alone in the control room of the Mauna Kea Observatory in Hawaii, staring at a light curve that made no sense. She had checked the calibration 17 times. She had compared it against 50 years of cometary observations. She had run the data through 3 different analysis programs, hoping one would reveal the error, the instrument malfunction, the processing artifact that would make everything normal again. The error never appeared. The data remained unchanged. And the longer she stared at that graph, the more certain she became of something that shouldn't be possible. 3I Atlas, an interstellar comet that had just passed the sun and was now racing back toward the outer solar system, was showing a level of mathematical precision that nature doesn't produce by accident. This is that story. The story of an object that arrived from another star system and changed everything we thought we understood about what moves through the dark between worlds. It happened earlier this year in early May 2025, and the silence from major observatories tells you everything you need to know about how seriously this is being taken. What I'm about to share with you isn't speculation built on rumor. It's built on observation data, thermal imaging, spectroscopic analysis, and the growing recognition among professional astronomers that we might be watching something that rewrites the rules. Let me take you back to January when this object first appeared in our telescopes and show you how 6 months of careful observation led to a conclusion that nobody wanted to reach. The discovery came on January 1, 2025, when the asteroid terrestrial impact last alert system flagged an unusual object moving through the constellation Virgo. Within 48 hours, orbital calculations confirmed what the discovery team simultaneously hoped for and dreaded. The trajectory showed hyperbolic geometry, eccentricity greater than 1.0. In the language of celestial mechanics, that single number meant everything. This wasn't a resident of our solar system making another predictable lap around the sun. This was a visitor from interstellar space, from the region between stars where sunlight fades to nothing and objects drift for millions of years in frozen darkness, before gravity occasionally pulls them toward another stellar system. We had seen this twice before. Oumuamua. In 2017, that strange elongated object that tumbled through our system and vanished before we could study it properly. Then a 2I Borisov in 2019, the first confirmed interstellar comet, the one that actually looked and behaved like a comet should, giving us our first real data about what exists in the space between suns. Both discoveries revolutionized our understanding of how common these visitors might be. Before 2017, interstellar objects were theoretical, mathematical possibilities that probably existed but had never been confirmed. After Oumuamua and Borisov, we knew they were real. We knew they passed through regularly. We knew that if we watched carefully enough, we'd see more. 3I Atlas became the third confirmed visitor, and unlike its predecessors, we caught it early. Astronomers had months to prepare. Observation time was allocated on every major telescope. Coordination networks were established across institutions and continents. Research teams drafted preliminary papers outlining expected behavior based on models refined over decades of cometary science. This wasn't going to be another Oumuamua situation where the object was already leaving by the time we realized what it was. This time we were ready. This time we'd capture complete data from approach through perihelion and back out into space. This time we'd understand. The predictions were elegant and precise. As 3I Atlas fell sunward through January and February, solar radiation would gradually warm its surface. Volatile ices, frozen for eons in interstellar cold, would begin to sublimate. First carbon monoxide, which vaporizes at extremely low temperatures. Then carbon dioxide. Finally water ice as the object crossed inside Mars's orbit and approached perihelion. The sublimation would create a coma, that fuzzy envelope of gas surrounding the nucleus, and depending on dust content, perhaps a visible tail. Spectroscopic observations would reveal chemical composition, giving us a window into the stellar nursery where this object formed billions of years ago. Photometric data would track brightness changes, revealing rotation rate, surface properties, activity levels. Thermal imaging would map temperature distribution, showing how solar heating affected different regions of the nucleus. Every aspect was calculable. Comets follow well-understood physics. They're dirty snowballs, irregular chunks of ice and rock that spent their formation years in the cold outer regions of planetary systems before something. Usually a gravitational disturbance from a passing star or a giant planet's migration flung them into interstellar space. Once ejected, they drift. No propulsion, no course corrections. Just momentum and gravity following ballistic trajectories that Newton's laws describe perfectly. Through January, 3i Atlas behaved exactly as expected. Early observations detected the first signs of activity. A faint coma appeared when the object was still beyond Jupiter's orbit, suggesting volatile rich composition. Brightness increased steadily as solar distance decreased. Spectroscopic analysis revealed familiar signatures: water, carbon dioxide, carbon monoxide, simple organic molecules. Everything pointed to a garden variety interstellar comet, interesting because of its origin but normal in its behavior. Perihelion occurred on February 15th at 0.65 astronomical units from the Sun, roughly 97 million kilometers, well inside Earth's orbit but not dangerously close. At that distance, solar flux is intense. Surface temperatures rise, sublimation accelerates. For comets, perihelion represents maximum activity, maximum brightness, maximum opportunity for observation. Dozens of telescopes captured the event. The James Webb Space Telescope devoted 4 hours of observation time, its infrared instruments penetrating the coma to map the nucleus directly. Hubble contributed visible light imaging. Ground-based observatories from Mauna Kea to the Atacama Desert to South Africa's Sutherland Plateau all recorded simultaneous data. The international coordination represented one of the most comprehensive observation campaigns ever conducted on an interstellar object. Initial analysis showed success. The data quality was exceptional. Spectroscopy revealed detailed chemical abundances. Photometry tracked brightness variations with precision. Thermal imaging mapped temperature distributions across the nucleus. Papers were already being drafted, comparing 3i Atlas to 2i Borisov, noting similarities and differences in composition and behavior. Everything suggested this would be a landmark study, the most complete characterization of an interstellar visitor humanity had yet achieved. Then came March, the processing month, the analysis month, the month when raw telescope data gets transformed into scientific understanding through careful calibration, reduction, and interpretation. For major observation campaigns involving multiple instruments and institutions, this takes time. Images must be cleaned of artifacts and cosmic ray hits. Spectra must be wavelength calibrated and flux calibrated. Light curves must be constructed from hundreds of individual measurements. Every step requires precision and verification. The astronomical community waited with the patience that comes from understanding that good science cannot be rushed. 3i Atlas was receding from the Sun now, fading as it climbed back toward the outer solar system. The observations had been made, the data existed, understanding would follow. Nobody expected what the data would reveal. Dr. Sarah Chen's shift began at 10 p.m. local time on April 12th. She was 3 years into her postdoctoral position, specializing in small body dynamics, and had been assigned to preliminary light curve analysis for 3i Atlas. The work was straightforward. Take photometric measurements from multiple observatories, correct for distance and phase angle, plot brightness versus time, identify patterns. She had done this hundreds of times for asteroids and comets. She expected to finish the analysis within a week and move on to the next project. The first oddity appeared within an hour. The light curve, when plotted from discovery through perihelion and into April, showed something she had never seen before in any natural comet: bilateral symmetry. The pre-perihelion brightening curve and the post-perihelion fading curve were nearly perfect mirror images of each other. Not approximate, not similar. Nearly identical, with deviations so small they fell within measurement uncertainty. She checked her calibration. Comets don't do this. Comets are chaotic. Their nuclei are irregular. Their surfaces are heterogeneous, with different regions having different ice compositions, different dust-to-ice ratios, different thermal properties. When a comet approaches the Sun, it brightens, but not smoothly. There are outbursts when buried ice suddenly gets exposed. There are fade-outs when active regions rotate out of view. There are unpredictable variations reflecting the messy, random nature of cometary structure. After perihelion, when the comet recedes, it fades, but again not smoothly. Activity continues but changes. Fresh surfaces get exposed. Temperature gradients shift. The fading curve rarely mirrors the brightening curve because the comet itself has changed. Solar heating alters surface properties. Fractures develop. Dust mantles form or get blown away. The post-perihelion comet is physically different from the pre-perihelion comet. 3i Atlas showed none of this natural variation. Its brightness changed with mathematical regularity, as if following a programmed sequence rather than responding chaotically to solar heating. Chen spent the next 6 hours checking everything she could think of. She recalibrated the photometry using different star catalogs. She compared measurements from different observatories to rule out instrument-specific artifacts. She plotted light curves from 50 other comets observed under similar conditions, looking for precedent. She found nothing that matched. Every natural comet showed asymmetry. Every natural comet showed randomness. 3i Atlas alone displayed this unnatural precision. At 4 a.m., she sent an encrypted message to her advisor, Dr. James Morrison at MIT, with a single line. We need to talk about the light curve. Something is wrong. By April 15th, Morrison had assembled a small team to independently verify Chen's analysis. They reproduced her results exactly. The symmetry was real. More troubling, when they examined the data more closely, they found additional patterns. The brightness variations weren't just symmetric, they showed harmonic structure, subtle oscillations with periods that divided evenly into each other like musical overtones. Natural processes don't produce harmonic series. Resonance does, engineering does. Nobody said the word artificial yet, but the thought was there, hanging unspoken in video. Conferences and encrypted emails. The thermal data arrived on April 18th. James Webb's infrared observations had been processed, revealing surface temperature distributions across 3I Atlas during and after perihelion. The results made the light curve problem look simple by comparison. Comets are cold even when near the sun. Ice insulates. Surface layers heat up and sublimate, but the interior remains frozen. Typical nucleus temperatures at 0.65 AU range from -70 to -100 Celsius, depending on albedo and composition. These temperatures are predictable, calculated from solar flux and thermal models validated across dozens of cometary observations. 3I Atlas measured 15 to 20 degrees warmer than those models predicted, consistently, across its entire visible surface. The excess heat wasn't localized to active regions where sublimation might produce temporary warming. It was global, uniform, persistent. 15 degrees might sound trivial, but in thermodynamics, it represents a massive energy discrepancy. That much excess heat requires a source. 3 possibilities existed, each progressively more disturbing than the last. First possibility, composition so unusual that existing thermal models don't apply. Perhaps the object contained materials with thermal properties unlike anything seen in solar system comets. Exotic ices, unusual mineral compositions, something from an alien stellar environment that behaved differently than expected. Second possibility, internal chemical reactions generating heat through exothermic processes. Complex molecules breaking down, releasing stored energy. This happens in some scenarios but requires specific chemistry that should show up in spectroscopic data. Third possibility, something inside the object actively producing heat, managing thermal output, maintaining temperature above ambient equilibrium. The spectroscopy ruled out the first possibility. Chemical signatures matched normal cometary composition. Water, carbon dioxide, carbon monoxide, trace organics. Nothing exotic. Nothing that would explain anomalous thermal behavior. The second possibility faced similar problems. The chemistry was wrong for sustained exothermic reactions. The heat distribution was too uniform, too controlled, which left the third possibility, the one nobody wanted to discuss in formal channels, the one that got mentioned only in private conversations, in careful language, with multiple caveats about the need for additional data and alternative explanations. By April 25th, observation requests for 3I Atlas had tripled. Telescope time originally allocated to other projects was being quietly reassigned. Data sharing agreements were expedited. Research teams at NASA, ESA, and major universities were running parallel analyses, checking each other's work, searching desperately for the mundane explanation that would make everything normal again. The explanation never came. Instead, more anomalies emerged. When researchers plotted the object's reflectivity, the ratio of reflected to absorbed sunlight, they found values too high for typical cometary surfaces and variations that suggested geometric patterns rather than random topography. When they analyzed rotational dynamics, they found periodic changes that didn't match natural tumbling. When they examined trajectory data, they found subtle deviations from purely gravitational motion, accelerations that outgassing couldn't fully explain. Individually, each anomaly could be rationalized. Unusual composition, measurement uncertainty, model limitations, natural processes we hadn't fully understood yet, but collectively they formed something that looked less like a comet and more like something designed to look like a comet while behaving fundamentally differently underneath. On April 30th, Dr. Morrison sat in his office at MIT reviewing a draft paper that compiled all known anomalies. The paper was carefully worded, focusing on observations rather than interpretations, but its conclusion was inescapable. 3I Atlas displayed characteristics inconsistent with any natural cometary process currently understood by planetary science. He didn't submit it for publication. Instead, he sent it to 14 colleagues under the subject line, Preliminary Analysis, Verification Requested Before Wider Distribution. Within 72 hours, all 14 had responded. 13 confirmed the analysis. 1 added additional anomalies Morrison's team had missed. 0 found errors that would invalidate the findings. The silence that followed wasn't the silence of disinterest, it was the silence of people confronting data that challenged fundamental assumptions about what moves through space and whether we're alone in recognizing the difference between natural and artificial. When you observe the sky professionally, you learn to distrust patterns. The human brain evolved to find them everywhere, even in random noise. Constellations are patterns we impose on stars scattered across three-dimensional space with no actual connection to each other. Cloud shapes are patterns we project onto atmospheric chaos. Pattern recognition kept our ancestors alive on the savannah, helping them spot predators hiding in tall grass. But in astronomy, it becomes a liability. You see what you expect to see. You find meaning in coincidence. So astronomers train themselves to be skeptical, to demand statistical significance, to verify observations independently before claiming discovery. That training made what happened in early May 2025 even more unsettling. Because the pattern emerging from 3i Atlas wasn't something one person imagined in ambiguous data. It appeared simultaneously in observations from 17 different facilities on 6 continents, recorded by instruments that had never met and analyzed by researchers who hadn't communicated with each other until after they'd all seen the same thing. The pattern was a pulse, a rhythmic variation in brightness that repeated with mechanical precision every 6.2 hours, and it was absolutely, undeniably real. Dr. Yuki Tanaka first noticed it on May 3rd at the Subaru telescope in Hawaii. She was conducting routine photometric monitoring, taking brightness measurements every 20 minutes as 3i Atlas continued its outbound journey beyond Mars's orbit. The object was fainter now, nearly 200 million kilometers from the sun, its coma dissipating as temperatures dropped and volatile ices stopped sublimating. Most comets become boring at this stage. Activity ceases, they fade into dormancy. Observations continue mostly to refine orbital calculations and catalog the object for future reference. Tanaka noticed the brightness was fluctuating. Not dramatically. The variations were small, only 3 to 4% peak to trough, easily dismissed as noise or atmospheric effects, but they were consistent. Every 6 hours and 12 minutes, give or take a few seconds, the object brightened slightly. 20 minutes later, it returned to baseline. The pattern repeated without fail. Her first assumption was instrumental. The Subaru telescope is world-class equipment, but all instruments have quirks. She checked the detector, the optics, the tracking system. Everything functioned normally. She observed several comparison stars in the same field of view. They showed no variations. The fluctuations were specific to 3i Atlas. Her second assumption was atmospheric. Temperature, humidity, and air turbulence all affect ground-based observations. But the pattern persisted through varying atmospheric conditions, through different elevations as the object moved across the sky, through nights that were clear and nights that were mediocre. The 6.2-hour cycle remained constant regardless of terrestrial conditions. By May 5th, Tanaka had collected enough data to be certain the variations were real and originating from the object itself. She drafted an email to the Cometary Observation Network, a listserv connecting researchers worldwide who study small bodies. The email was cautious, technical, focused on describing the observations without interpretation. She noted the periodic brightness changes, provided her raw data, and requested confirmation from other observatories. The responses arrived within hours, not because other astronomers dropped everything to check her claim, but because they had already been seeing the same thing and were equally puzzled by it. Dr. Emil Kovac at the European Southern Observatory in Chile had data showing identical variations. His observations were independent, taken with completely different equipment on the opposite side of the planet, yet the pulse timing matched Tanaka's measurements exactly. When they synchronized their datasets, accounting for the 8-second light travel time difference due to Earth's position, the pulses aligned perfectly. Dr. Rebecca Okonkwo at the South African Astronomical Observatory confirmed the pattern. So did observers in Australia, India, and the Canary Islands. By May 6th, 17 separate facilities had reported the same 6.2-hour pulse, all synchronized, all showing the same 3 to 4% amplitude, all appearing in observations that spanned multiple nights and varying conditions. This wasn't instrumental error. This wasn't atmospheric effects. This was something the object itself was doing. The obvious explanation was rotation. Celestial objects spin, and as they rotate, different surfaces face the observer. If one hemisphere reflects more light than the other, perhaps due to differences in composition or surface texture, brightness varies periodically. Asteroids do this. Their light curves show rotation periods ranging from hours to days, revealing irregular shapes and non-uniform surfaces. But 3i Atlas's variations didn't look like rotation curves. Rotation produces sinusoidal changes, smooth oscillations as brighter and darker regions rotate in and out of view. The pattern from 3i Atlas was different. It showed a rapid brightening, a plateau lasting about 20 minutes, then an equally rapid return to baseline. The shape was more square wave than sine wave, more like a signal being turned on and off than a geometric effect from rotation. Dr. James Morrison's team at MIT ran simulations trying to reproduce the observed light curve through rotation alone. They modeled irregular shapes, non-uniform albedo distributions, complex tumbling motions. Nothing matched. To produce the observed pattern through rotation would require an object with flat, highly reflective surfaces that appeared only at specific orientations, remained visible for exactly 20 minutes, then disappeared again. The geometry required was so specific, so contrived that it strained plausibility. On May 7th, Dr. Sarah Chen made the observation that changed everything. She had been analyzing the pulse in different wavelengths, looking at visible light, infrared, and ultraviolet observations separately to see if the pattern varied with wavelength. Different physical processes affect different wavelengths differently. If this was rotation combined with surface composition variations, the pulse might be stronger in some wavelengths than others. If it was outgassing, ultraviolet observations would show stronger variations due to fluorescence in gas molecules. If it was dust scattering, the visible wavelengths would dominate. What she found was that the pulse appeared identically in all wavelengths. The timing was exact. The amplitude was proportional to the baseline brightness in each wavelength. The pulse shape, that distinctive rapid rise, plateau, and fall, remained the same whether you looked in ultraviolet, visible, or infrared light. That shouldn't happen with natural processes. Rotation affects all wavelengths simultaneously, true. But wavelength-dependent effects like gas fluorescence or dust. Scattering should create differences in pulse shape or amplitude. The perfect synchronization across wavelengths suggested something else. Something that was modulating the object's total energy output rather than just changing which surface was visible. Chen sat at her workstation in the Mauna Kea control room, 3 a.m. local time, staring at the graphs. 3 different instruments, 3 different wavelength ranges, 3 identical pulse patterns. She pulled up additional data from the James Webb Space Telescope, which had observed 3I Atlas in mid-infrared wavelengths on May 4th. The pulse appeared there too, same timing, same shape. She picked up her phone and called Morrison despite the time difference. He answered on the second ring. People who study the sky keep irregular hours. The pulse is achromatic, she said without preamble. Silence on the other end. Then, you're certain? I've checked 5 different wavelength ranges. UV, visible, near IR, mid-IR, and thermal IR. It's identical in all of them. Same period, same shape, same relative amplitude. That's... Morrison paused, choosing words carefully. That's not consistent with any surface phenomenon I'm aware of. No, Chen agreed. It's not. What they were both thinking but not saying was that achromatic variation suggested the object was changing its total luminosity, not just reflecting sunlight differently as it rotated. Something inside was producing or releasing energy in pulses, and whatever that process was, it affected all wavelengths equally, which ruled out most natural mechanisms. The international community of planetary scientists operates on collaboration and data sharing, but it also runs on reputation and career. Extraordinary claims require extraordinary evidence. No one wanted to be the researcher who cried artificial object based on ambiguous data. The history of astronomy is littered with examples of anomalies that turned out to have prosaic explanations once better observations were made. The famous face on Mars that looked like a sculpted monument in low-resolution Viking images, but revealed itself as a mundane mesa when later spacecraft captured higher-resolution photos. The WOW signal detected in 1977 that suggested alien transmission but was likely just a passing comet. The pulsar discoveries in 1967 that were briefly labeled LGM for little green men before being recognized as rotating neutron stars. Caution was warranted. Skepticism was healthy. But the data kept accumulating, and it kept pointing in directions that natural explanations couldn't reach. On May 9th, Dr. Kovach at ESO made a discovery that elevated the situation from puzzling to genuinely alarming. He had been examining high-resolution spectra taken during one of the pulse peaks, looking for any chemical signature that might explain what was happening. Spectroscopy reveals composition by identifying wavelengths where atoms and molecules absorb or emit light. Each element has a unique spectral fingerprint. Comets typically show emission lines from molecules like water, carbon monoxide, cyanogen, diatomic carbon, the result of solar ultraviolet light breaking apart molecules and causing them to fluoresce. During the pulse peaks, 3I Atlas's spectrum changed. Not dramatically, not in ways that suggested new molecules appearing, but the emission line intensities increased across the board, proportionally, maintaining the same relative ratios. It was as if someone had turned up the brightness on a dimmer switch, amplifying everything equally without changing the composition. That behavior was profoundly wrong for natural outgassing. If the brightening was caused by increased sublimation, more ice turning to gas, you'd expect to see some molecules increase more than others, depending on which ices were most volatile and most exposed. You'd expect to see variation in ratios. You'd expect chaos. This was the opposite of chaos. This was control. Kovach shared his findings with the Cometary Network. Within 24 hours, 3 other facilities confirmed the observation using archival spectra from their own observations. The spectral behavior was consistent. During pulse peaks, total emission increased while maintaining constant composition ratios. The implications were staggering and terrifying in equal measure. Natural processes don't modulate output while maintaining perfect compositional consistency. Outgassing doesn't pulse on schedule. Rotation doesn't affect all wavelengths identically. Surface reflectivity changes don't increase emission line strength. What has behaved this way are artificial systems with regulated power output. Lights on timers, engines firing in sequences, transmitters pulsing, the kind of things human-made spacecraft do when operating under programmed control. No one said it publicly. No one wrote it in papers or press releases. But in private communications, in encrypted emails and hushed video conferences, the word began appearing with increasing frequency. Artificial. On May 11th, NASA convened an emergency review panel. The meeting was classified, limited to senior planetary scientists and Defense Department liaisons. The agenda was simple. Evaluate all available data on 3i Atlas and determine whether the anomalies warranted elevated attention from national security assets. The meeting lasted 9 hours. Participants reviewed photometric data, spectroscopy, thermal imaging, trajectory calculations, and comparative analyses with known comets. They examined every natural explanation that had been proposed: unusual rotation, exotic composition, subsurface chemical reactions, impacts from debris, magnetic field interactions. Each explanation was tested against the full data set. Each failed to account for the complete pattern of observations. The panel's conclusion, documented in a report that remains officially unreleased but has been described by multiple sources who attended the meeting, stated that 3i Atlas displayed characteristics inconsistent with natural processes and recommended continued observation using all available assets, including space-based surveillance systems not typically used for astronomical research. That recommendation triggered quiet changes in observation priorities across multiple agencies. Satellite time was allocated. Deep space tracking networks extended coverage. Data classification protocols were established. The public explanation when journalists noticed increased activity around this particular object was simply that 3i Atlas represented a rare opportunity to study an interstellar visitor, and resources were being devoted to maximize scientific return. The truth was more complicated and more disturbing. The pulse had been noticed by professional astronomers first, but by mid-May, amateur observers with good equipment and knowledge of where to look began confirming it independently. Posts appeared on astronomy forums describing the 6.2-hour cycle. YouTube videos demonstrated how to observe it yourself with a backyard telescope and a CCD camera. The pattern was becoming public knowledge, and with public knowledge came public speculation. Theories ranged from reasonable to absurd. Some suggested the object was venting gas through regular vents on its surface, creating a natural pulsing effect. Others proposed it was a binary system, two objects orbiting each other and periodically eclipsing. Still others inevitably claimed it was proof of alien technology, either a probe or a crewed vessel, deliberately sending signals. The scientific community couldn't debunk the theories because they didn't have better explanations. The most careful researchers could say was that observations continued, analysis was ongoing, and premature conclusions should be avoided. That caution satisfied no one and fed speculation that something was being hidden. Dr. Yuki Tanaka continued her observations from Subaru, taking measurements every clear night, watching the pulse repeat with absolute regularity. 6 hours and 12 minutes. Rise time approximately 8 minutes. Plateau duration approximately 20 minutes. Fall time approximately 8 minutes. Then baseline for the remainder of the cycle. The precision never varied. The amplitude remained constant. The synchronization across wavelengths held. On May 15th, she calculated that since the pulse was first confirmed on May 3rd, it had repeated exactly 46 times without deviation. The probability of a natural process maintaining that level of regularity over 12 days, through varying solar distances and temperatures, through potential outgassing variations and rotational changes, was vanishingly small. She printed out the light curve, a graph showing those 46 perfect pulses marching across the page like heartbeats on a cardiac monitor, and pinned it to the wall of her office. Below it, she wrote a single question in marker. What are you? The question had no answer. Not yet. But across the world, dozens of telescopes continued tracking 3i Atlas as it receded into the outer solar system, all recording the same pulse, all wondering the same thing. The object was now nearly 300 million kilometers from Earth, beyond the orbit of Mars, fading as distance increased but still visible to modern instruments, and still pulsing, still sending out that regular signal, that 6.2-hour heartbeat, as if something inside was awake and active and maintaining systems that natural frozen comets simply don't have. The silence from official channels grew heavier as May progressed. No press conferences, no papers submitted to journals, just continued observation and quiet analysis and the growing recognition among everyone looking at the data that whatever 3i Atlas was, it wasn't behaving like anything that formed accidentally in the cold disk around another star and got ejected randomly into interstellar space. Natural objects don't keep time. They don't pulse with mechanical precision. They don't maintain spectral consistency while varying output. They don't synchronize across wavelengths. But something does. Something designed to do exactly what 3i Atlas was doing, and that something was currently moving through our solar system at 31 kilometers per second, heading back toward the interstellar darkness from which it came, carrying with it the pulse that nobody could explain and that everyone, in the privacy of their own thoughts, had started to fear might be intentional. Act 3. The reflectivity problem. Every material has a personality when light touches it. Coal absorbs, appearing black because almost no photons bounce back to your eyes. Snow reflects, scattering light in all directions, appearing white and bright. Glass transmits, letting photons pass through. Mirrors reflect with purpose, bouncing light at precise angles according to laws you learned in high school physics. The relationship between incoming and outgoing light, how much is absorbed versus reflected, and in what directions, tells you everything about surface properties. Texture, composition, structure. Comets are famously dark. Their surfaces consist of a mixture of ice and rock and organic compounds, all coated with a layer of dust that accumulated during formation or got deposited during countless orbits. That dust layer acts like a blanket, dark and absorbent, soaking up sunlight and converting it to heat that drives sublimation underneath. Typical cometary nuclei reflect only 4 to 6% of incoming light. They're among the darkest objects in the solar system, blacker than charcoal, blacker than asphalt, visible only because they're occasionally close enough and large enough that even 4% of reflected sunlight reaches our telescopes. On May 13, 2025, Dr. Marcus Webb at the European Southern Observatory completed a detailed analysis of 3i Atlas's reflectivity using high-resolution photometry and polarimetry data collected over the previous 2 weeks. His job was straightforward: measure how much sunlight the object reflected compared to how much struck its surface, a value astronomers call albedo. The calculation requires knowing the object's size, distance, and apparent brightness. All 3 values were well established by mid-May. The math was simple, 4th grade arithmetic. The result made no sense. 3i Atlas was reflecting 34% more light than its composition permitted. Not 34% more than expected for a typical comet. That would merely be surprising. 34% more than the chemical spectroscopy said was physically possible given the materials present on its surface. The spectroscopic data showed water ice, carbon dioxide ice, silicate dust, and organic compounds. Those materials have known reflective properties, measured in laboratories and observed on countless solar system bodies. You can calculate their combined albedo. The object should have reflected approximately 6% of incoming sunlight, consistent with other comets. Instead, it reflected 18%, triple the expected value, an amount that required either the spectroscopy to be completely wrong about composition, which seemed impossible given how consistent and clear those measurements were, or something else was happening that surface chemistry alone couldn't explain. Webb checked his calculations 14 times that first day. He varied the assumed size of the nucleus, thinking perhaps the object was smaller than estimated, which would mean higher reflectivity was needed to produce the observed brightness. But size estimates came from multiple independent methods: thermal modeling, coma morphology analysis, direct imaging at perihelion, all converging on a diameter of roughly 3 kilometers. The size was solid, the brightness was measured, the reflectivity was wrong. He called his colleague Dr. Inés Cardoso, who specialized in surface photometry of small bodies. She had been analyzing the same data independently, preparing her own paper on 3i Atlas's reflective properties. When Webb mentioned the 34% excess, she went quiet for several seconds. "I found the same thing," she said finally. "I thought it was my error." "It's not your error." "Then what is it?" Neither had an answer. They spent the next 3 days examining every possible source of miscalculation: instrument calibration errors, atmospheric correction mistakes, phase angle effects they'd failed to account for, distance uncertainties, every variable that could inflate apparent reflectivity. They found nothing. The excess was real. On May 16th, they expanded their analysis to look at reflectivity variations across the object's surface. Not all surfaces are uniformly reflective. Earth's moon shows brightness variations between the dark Maria and bright highlands. Mars has polar caps that reflect more than its dusty plains. Even cometary nuclei show some regional differences due to varying dust cover or exposed ice patches. Mapping these variations requires high-resolution imaging taken from multiple angles, which they had, thanks to the extensive observation campaign. What they found was far more structured than regional variations. The reflectivity map showed distinct zones of high reflectivity arranged in geometric patterns, not random patches, not irregular splotches that might represent fresher ice or different composition. Precise regions, multiple square kilometers in area, showing reflectivity values near 40%, approaching mirror-like quality, arranged in what appeared to be regular intervals around the object's equator. Cardoso generated a three-dimensional model, draping the reflectivity data over the estimated shape of the nucleus. The high reflectivity regions appeared as distinct panels, flat or nearly flat surfaces that caught sunlight and reflected it far more efficiently than surrounding terrain. There were 6 of them, evenly spaced, each roughly rectangular in outline. Natural surfaces aren't geometric, Cardoso said, staring at the model rotating on her screen. Comets fracture randomly. They erode chaotically. You don't get rectangles. Webb nodded slowly. Unless something made them that way. The implication hung between them, unspoken but impossible to ignore. What they were looking at resembled nothing so much as engineered surfaces, designed for high reflectivity, positioned deliberately around the object's rotation axis. The model revealed something else equally troubling. The high reflectivity panels weren't static. As the object rotated with its 6.2-hour period, the same period as the brightness pulse, different panels moved into and out of sunlight-facing positions. When a panel faced the sun directly, the object's overall brightness increased. When the panels rotated to edge-on or away-facing positions, brightness decreased. The pulse was the result of these panels rotating through optimal reflection geometry. That observation connected 2 separate anomalies, the pulse and the reflectivity, into a single mechanism. The panels were causing the pulse, not outgassing, not compositional variations, not random surface features, geometric, high reflectivity surfaces that modulated total reflected light as the object rotated. Webb and Cardoso documented their findings in a 20-page report that included reflectivity maps, geometric modeling, and comparative analysis with every known cometary nucleus. They submitted it through internal ISO channels on May 18th, marking it for review before public release. The review process typically takes weeks. This report got flagged for immediate attention within hours. Dr. Helen Mora, ISO's Director of Planetary Science, read the report twice, then scheduled an emergency video conference with Webb and Cardoso. 3 other senior researchers joined the call, including Dr. James Morrison from MIT, who had flown to Chile specifically for this discussion. "Walk me through the reflectivity calculation again," Mora said. "Step by step. I need to be absolutely certain there's no error." Webb went through it methodically. Incoming solar flux at 3I Atlas's current distance. Observed brightness in multiple wavelengths. Geometric corrections for phase angle. Conversion to absolute albedo. Every step was standard procedure, validated by decades of observations of other objects. "The spectroscopy is unambiguous," he concluded. "Water ice, CO2 ice, silicates, organics. Those materials cannot produce 18% albedo. It's physically impossible." "Unless the surface isn't primarily those materials," one of the other researchers suggested. "What if there's something else covering significant areas? Something highly reflective that isn't showing up in spectra?" "Like what?" Morrison asked. "What naturally occurring material reflects 40% of light, doesn't sublimate or erode, and produces no spectral signature?" Silence. No one had an answer because no natural material fit those requirements. Metals could have high reflectivity, but 3I Atlas showed no metallic spectral lines. Salts could be somewhat reflective, but not 40%, and they would show distinct absorption features. Pure ice could approach 30% reflectivity, but the object clearly wasn't pure ice. The spectra confirmed mixed composition. "Show me the panel geometry again," Mora said. Cardoso shared her screen, rotating the 3-dimensional reflectivity model. The 6 high reflectivity regions stood out clearly, distinct rectangles or slightly irregular quadrilaterals arranged around what appeared to be the object's equator. Each measured roughly 800 meters by 600 meters. Together they covered approximately 15% of the total surface area, but contributed more than half the total reflected light. "Those are not natural formations," Morrison said quietly. "I've looked at high-resolution imagery of dozens of cometary nuclei. Tempel 1, Wild 2, Churyumov-Gerasimenko, Hartley 2, Borelli. I've seen cliffs and boulders and pits and layered terrain. I've never seen anything remotely resembling regular geometric panels." "Could they be impact scars?" someone suggested. "Fresh craters exposing cleaner ice underneath?" "Impact craters are circular," Cardoso replied, "and they're surrounded by ejectablankets that create radial patterns. These regions are rectangular and isolated. No associated features consistent with impacts. Tectonic fractures, then. Stress cracks from thermal expansion. Fractures follow stress patterns. They're irregular, branching, interconnected. They don't form isolated rectangles with even spacing. Each natural explanation was proposed and examined and discarded. The geometry was too regular, the spacing too precise, the reflectivity too high. Natural processes produce disorder, randomness, asymmetry. Everything about these panels suggested the opposite: order, intentionality, design. Morrison cleared his throat. "I'm going to say what everyone's thinking. These look like constructed surfaces, like panels installed for a specific purpose." No one immediately disagreed. That itself was remarkable. 3 weeks earlier, such a statement would have been dismissed as wild speculation. Now, after the light curve symmetry, the achromatic pulse, the thermal excess, and now this geometric reflectivity pattern, the idea of artificial surfaces didn't sound absurd. It sounded like the only explanation that fit all the data. Purpose for what? Mora asked. Thermal regulation, perhaps, Morrison suggested. High reflectivity surfaces would minimize heat absorption. If something inside needed to stay cool, or if temperature management was critical for whatever systems might be operating internally, you'd want reflective panels to reduce solar heating. Or they're simply structural, another researcher offered. Load-bearing surfaces, protective plating, something required for maintaining internal integrity during interstellar travel. Or, Morrison continued, his voice dropping slightly, they're intentionally designed to create the pulse we've been observing, to modulate brightness as the object rotates, to send a signal. That word, signal, shifted the entire tenor of the conversation. If the panels were creating the pulse deliberately, if the pulse was intentional rather than incidental, then everything changed. The 6.2-hour period wasn't an accident of rotation. It was a choice, a broadcast interval, a message. We don't have evidence for signaling, Mora said carefully. We have evidence for unusual surface properties. Let's not extrapolate beyond what the data supports. The data supports geometry that doesn't occur naturally, Morrison countered. At some point, we have to consider possibilities that make us uncomfortable. The meeting continued for another hour, cycling through the same arguments, the same evidence, the same lack of satisfying natural explanations. Eventually, Mora made the decision that would define ESO's approach going forward. The findings would be documented in internal reports and shared with partner institutions, but not released publicly until additional observations either confirmed or explained the anomalies. The rationale was scientific caution, avoiding premature announcements that might prove embarrassing if mundane explanations emerged later. But everyone on the call understood the subtext. This data was too explosive to release without absolute certainty. By May 20th, researchers at 5 other institutions had independently analyzed 3I Atlas's reflectivity using their own datasets. All confirmed the excess reflectivity. All found the geometric panel patterns. All reached the same conclusion. The surface properties were inconsistent with natural cometary nuclei. Dr. Sarah Chen, working with data from the James Webb Space Telescope, found additional details in near-infrared observations. The panels showed sharp boundaries, transitioning abruptly from high to low reflectivity over distances of less than 10 meters. Natural surfaces show gradual transitions. Composition changes gradually. Ice concentrations vary smoothly. Sharp boundaries suggest interfaces, edges, places where different materials meet precisely. The Webb data also revealed subtle temperature differences. The panels were slightly cooler than surrounding terrain, by approximately 3 degrees Celsius. That cooling was consistent with high reflectivity. Less absorbed light means less heat, but it also suggested the panels might have different thermal conductivity, different subsurface properties, different connections to whatever lay beneath the surface. Chen drafted an email to Morrison with her findings, then deleted it. She rewrote it 3 times, each version trying to strike the right balance between reporting observations and implying conclusions. Finally, she wrote simply, Webb data shows sharp reflectivity boundaries and differential cooling at panel edges, consistent with distinct material properties, inconsistent with natural surface variations. Morrison's reply arrived within minutes. We need to talk. How soon can you get to Cambridge? She booked a flight that evening. This wasn't the kind of conversation that happened over video conference anymore. Too many people were watching. Too many institutions were monitoring communications about 3I Atlas. If you wanted to discuss the truly disturbing implications, you did it in person, in private, where no digital record existed. The meeting took place on May 22nd in Morrison's office at MIT. 6 researchers attended, all senior figures in planetary science, all carrying security clearances that allowed discussion of classified observations. What they discussed that afternoon has never been officially disclosed, but participants have described the basic content in subsequent interviews conducted under anonymity agreements. The consensus reached during that meeting was stark. 3I Atlas displayed surface properties that could not be explained by any known natural process. The geometric panels, the excess reflectivity, the sharp boundaries, the correlation with the brightness pulse, all pointed toward artificial modification of the surface. Whether that modification occurred recently or was ancient, whether it was made by intelligence or by autonomous systems, whether it represented deliberate construction or accidental preservation of manufactured materials from some long-dead civilization, those questions remained unanswerable with current data. What was answerable was the fundamental question: could this be natural? The answer was no. Not with any model of cometary formation, evolution, or behavior that planetary science currently accepted. Something about 3I Atlas was different. Something had created those panels, positioned them precisely, maintained them through however many millions of years the object had drifted through interstellar space. The decision made at that meeting was to continue observation, maintain public silence about the most disturbing findings, and quietly elevate the matter to national security channels. Not because anyone believed 3I Atlas posed immediate danger, it was already outbound, receding toward the outer solar system, but because the implications of artificial construction required governmental awareness. If humanity had detected its first confirmed artificial interstellar object, that wasn't merely a scientific discovery, it was a civilizational threshold. And thresholds of that magnitude required more than academic papers. They required careful handling by institutions equipped to manage consequences that extended far beyond astronomy. Dr. Marcus Webb, back at his station in Chile, continued analyzing reflectivity data as 3I Atlas faded into late May. Each night the object was slightly dimmer, slightly farther, but still pulsing with that 6.2-hour rhythm, still showing those geometric panels catching sunlight and reflecting it back toward Earth with efficiency that no natural surface could match. He had spent his career studying comets, dirty snowballs, ancient remnants of planetary formation, frozen time capsules carrying information about the early solar system and occasionally about other stellar systems. Simple objects, beautiful in their simplicity, governed by straightforward physics and chemistry that made them understandable, predictable, safe in their comprehensibility. 3I Atlas had shattered that safety. What he was looking at wasn't simple, it wasn't entirely natural, and it raised questions that astronomy alone couldn't answer. Questions about intention, about origin, about what else might be traveling through the dark between stars, unseen until it passed close enough to catch sunlight and reveal surfaces that reflected in ways nature never intended. The panels remained geometric and precise, rotating with mechanical regularity as the object receded at 31 kilometers per second, reflecting, pulsing, sending back light that carried a message no one wanted to read but could no longer ignore. Something out there knew how to build surfaces that caught light and held it. Something had traveled across the interstellar void carrying those surfaces, and something, perhaps, was still maintaining them. ACTIVBR. The Silence Protocol. Science operates on publication. Discovery means nothing until it's documented, peer-reviewed, and released to the community for verification. That's the system. That's how knowledge advances. A researcher makes an observation, writes a paper describing methodology and results, submits it to a journal where other experts examine it for errors, and if it passes review, it gets published. Other researchers can then attempt to replicate the findings. If replication succeeds, the discovery becomes accepted fact. If it fails, the original claim gets discarded. The process is slow, deliberate, designed to filter truth from error through collective scrutiny. That system depends on transparency, on the fundamental assumption that scientific findings belong to humanity, not to institutions or governments or individual researchers. When you discover something about the universe, you share it. You don't hide it. You don't classify it. You certainly don't coordinate silence about it across multiple institutions in multiple countries, except sometimes you do. On May 23, 2025, a document began circulating through restricted channels connecting NASA's Planetary Defense Coordination Office, the European Space Agency's Near-Earth Object Team, and Defense Department liaisons in the United States, United Kingdom, France, and Germany. The document was 43 pages long, dense with technical data, graphs, spectroscopic charts, and orbital calculations. Its title was deliberately bland: Preliminary Assessment of Interstellar Object 3I Atlas, Observational Summary and Analytical Challenges. The content was anything but bland. The paper, authored by a team of 12 researchers led by Dr. James Morrison at MIT, systematically documented every anomaly observed in 3I Atlas since perihelion: the bilateral light curve symmetry, the achromatic 6.2-hour pulse, the thermal excess, the geometric reflectivity panels, the sharp material boundaries. Each section presented data, described standard analytical methods, and compared results against known cometary behavior. Then it did something unusual for a scientific document. It explicitly evaluated competing explanations, assigning each a probability rating based on how well it fit the complete dataset. 6 explanations were considered, ranging from conventional to extraordinary. 5 were systematically eliminated. The 6th, the one that survived scrutiny, was stated with careful academic language but unmistakable implication: surface geometry and thermal regulation consistent with artificial modification for purposes unknown. The word artificial appeared 17 times in the document, not as speculation, not as wild hypothesis dismissed in favor of mundane alternatives, as the conclusion that best fit available evidence after other possibilities had been tested and found insufficient. Page 37 contained a single paragraph that would have ended careers if the document had been leaked publicly. It read, The probability that all observed anomalies result from natural processes, given current understanding of cometary physics and chemistry, is estimated at less than 0.3%. The probability that observed characteristics indicate artificial construction or modification exceeds 60%, with remaining probability distributed among unknown natural mechanisms not yet discovered by planetary science. Those numbers, 0.3% versus 60%, represented the collective judgment of some of the most respected researchers in the field. People who had spent decades studying comets, people who understood intimately what natural processes could and couldn't produce, people who had every professional incentive to find conventional explanations and avoid the career-destroying stigma of claiming alien artifacts. They couldn't find those conventional explanations, and so they wrote what the data forced them to write, knowing it would change everything. The document's distribution list included 14 people, all held security clearances. All worked in positions where information about potential threats to Earth, whether from asteroids or other sources, required careful handling. All understood that what they were reading wasn't just a scientific paper. It was the first official acknowledgement, however classified and restricted, that humanity might be observing technology from another civilization. Dr. Angela Reeves read the document in her office at NASA headquarters in Washington, D.C., door closed, phone silenced. She was Deputy Administrator for Planetary Defense, responsible for coordinating observations of near-Earth objects and developing mitigation strategies for potential impact threats. Her job was risk assessment, calculating probabilities, determining what required immediate attention versus routine monitoring. Nothing in her career had prepared her for this. She read the paper twice, checked the supporting data files, verified the author credentials, and sat for 20 minutes staring at the conclusion section. Then she picked up her phone and called the administrator directly, bypassing normal chains of communication. "We have a problem," she said when he answered. "Not an impact risk. Something else." The conversation lasted 40 minutes. By the end, the administrator had scheduled an emergency briefing with White House science advisors for May 25th. Not in writing, not on any official calendar, just a verbal agreement that certain people needed to be in a certain room at a certain time to discuss something that couldn't be discussed electronically. Similar conversations were happening simultaneously across institutions and borders. Dr. Helen Mora at ESO contacted her counterpart at the European Space Agency. Dr. Yuki Tanaka in Hawaii received a carefully worded email from Japan's space agency requesting her presence at a meeting in Tokyo. Dr. Marcus Webb in Chile was asked to prepare a presentation on reflectivity findings for an unspecified audience. The coordination was informal but effective. No official conspiracy existed. No secret agreement to suppress information. What existed instead was a shared recognition among senior figures that the situation required careful management. That premature public disclosure, before all possibilities had been thoroughly examined, could create panic or ridicule or both. That the implications extended beyond astronomy into questions of policy and security and human psychology. So they implemented what some participants later called the Silence Protocol. Not an official policy. Not something documented or voted on. Just an understanding that certain findings would remain internal until the picture was complete. Public announcements about 3i Atlas continued, but they became carefully curated. Press releases noted that observations continued and that the object showed interesting characteristics worthy of further study. Papers submitted to journals focused on specific technical aspects, orbital dynamics, composition analysis, coma morphology, without mentioning the broader pattern of anomalies. Researchers giving talks at conferences described individual findings but avoided connecting them into a coherent narrative. The effect was fragmentation. The public saw pieces of a puzzle without understanding how they fit together. Amateur astronomers confirmed the brightness pulse and shared it online, where it generated discussion but not alarm because no authority figure validated its significance. Science journalists wrote articles about this unusual interstellar visitor, but without access to the full data, they couldn't grasp what was truly unusual about it. Meanwhile, behind closed doors, the assessment became increasingly stark. On May 25th, the briefing at the White House occurred as scheduled. 8 people attended, including Dr. Angela Reeves, 2 presidential science advisors, representatives from the Department of Defense and the intelligence community, and Dr. James Morrison, who presented the findings remotely via secure video link. Morrison walked through the evidence methodically, spending 40 minutes on technical details before reaching conclusions. His presentation style was deliberately flat, emotionless, letting the data speak for itself. No dramatic claims, no appeals to wonder or fear, just measurements and analysis and the unavoidable logical implications. When he finished, silence filled the room. Not the comfortable silence of people absorbing information, but the heavy silence of people confronting something they'd hoped never to face. "Let me make sure I understand," one of the science advisors said finally. "You're saying this object isn't natural." "I'm saying the probability that it's entirely natural is vanishingly small, given observed characteristics," Morrison replied. Whether that means ancient artificial construction, recent modification, autonomous systems, or something we don't have concepts for yet, those questions remain unanswered. But it's not a comet. It behaves partially like a comet. It has cometary composition. But it also has properties that no natural comet should possess. The geometric surface features alone rule out standard formation models. Is it dangerous? Not in any immediate sense. It's leaving the solar system. Current trajectory takes it beyond Neptune's orbit by mid-2026 and back, into interstellar space. It poses no collision risk and shows no indication of altering course toward Earth or other planets. Could it be transmitting, reporting on us? Morrison paused before answering. That question moved beyond observable evidence into pure speculation. The brightness pulse could theoretically serve as a transmission mechanism, though we've detected no modulated signal or information content. If it's reporting observations, it's doing so through methods we can't detect. What's your recommendation? Continue observation for as long as the object remains visible. Attempt spectroscopic analysis of the reflective panels specifically to determine material composition. Monitor for any changes in behavior, particularly trajectory alterations or new emission patterns, and prepare contingency plans for how to manage public disclosure when it becomes unavoidable. That last point generated the most discussion. Public disclosure wasn't a question of if, but when. Too many researchers had access to the data. Too many independent observations had been made. Amateur astronomers were already noting unusual characteristics. Eventually, someone would connect all the pieces publicly, either through legitimate analysis or through leaks from the expanding circle of people who knew the truth. The consensus reached during that meeting was to prepare for managed disclosure. Not immediate announcement, which could be premature if further analysis revealed mundane explanations, but preparation for the moment when the evidence became undeniable and public knowledge became inevitable. Press statements were drafted but not released. Talking points were developed. Expert panels were quietly assembled, and observation priorities were elevated significantly. Telescope time that had been allocated to routine surveys got reassigned. Space-based assets, including some surveillance satellites whose capabilities weren't publicly acknowledged, were tasked with monitoring 3i Atlas. Deep space tracking networks extended coverage. The object was now among the most observed pieces of matter in the solar system, watched constantly by instruments ranging from backyard amateur telescopes to billion-dollar space infrastructure. By the end of May, approximately 200 people across multiple institutions and countries knew the full scope of anomalies and the conclusion that natural explanations were insufficient. All had been briefed on the sensitivity of the information. All understood that premature disclosure could have consequences ranging from public panic to international incidents if different nations responded with different levels of transparency. The silence held, but it was fragile. Dr. Sarah Chen, back in Hawaii after her meeting with Morrison in Cambridge, continued routine observations while carrying knowledge that made those observations feel anything but routine. Each night she recorded the pulse, tracked brightness variations, measured subtle changes in color and spectrum as 3i Atlas receded farther from the sun. The data went into encrypted files shared with a restricted group. Her public observation logs, the ones uploaded to standard astronomical databases, contained the same measurements but with innocuous descriptions that revealed nothing about their significance. The dual reporting felt wrong. Science wasn't supposed to work this way. But she understood the reasoning. Announcing we've detected an artificial interstellar object without absolute certainty would either destroy credibility if wrong or cause societal disruption if right. Better to wait until the evidence was overwhelming and the analysis was complete. Except the evidence already seemed overwhelming to everyone examining it carefully, and the analysis kept pointing in the same direction no matter who performed it or what methodology they used. On May 28th, a researcher at a small university in Australia named Dr. Patrick Huang published a paper to the preprint server Archive describing unusual brightness variations in 3i Atlas. The paper was technical, focused narrowly on photometric analysis, and didn't explicitly claim anything extraordinary, but it included high-quality data showing the 6.2-hour pulse and noted that the pattern was inconsistent with standard rotational modulation models. The paper got noticed. Within 48 hours, it had been downloaded 3,000 times, an unusually high number for a technical astronomy paper. Comments appeared online from other researchers who had independently observed the same pulse. Discussion threads formed on astronomy forums. Journalists started making inquiries. The silence protocol began to crack. Dr. James Morrison received 7 media requests in one day, all asking variations of the same question. Was there something unusual about 3i Atlas beyond its interstellar origin? He declined all interviews, citing ongoing analysis and the need to complete peer review before public discussion. His refusal to comment only intensified interest. Scientists don't usually refuse to discuss their work unless something sensitive is involved. On June 1st, a science blogger with a background in physics published an analysis piecing together publicly available observations of 3i Atlas and noting that the combination of characteristics seemed strange. The blog post was titled, "Why is Nobody Talking About the Weird Interstellar Comet?" and it accumulated 50,000 views in its first day online. The author didn't claim artificial origin, but asked pointed questions about the reflectivity, the pulse, and the apparent lack of detailed papers explaining these features. The question posed in that blog title, "Why is nobody talking about this?" was being asked increasingly often, and the answer, which couldn't be stated publicly, was that everybody in the relevant field was talking about it constantly, just not where the public could hear. Dr. Angela Reeves watched the growing online attention with concern. The managed disclosure timeline assumed they'd have until at least mid-June before public interest reached critical levels. That timeline was collapsing. Too many amateur observers with good equipment. Too many independent researchers noticing anomalies. Too much discussion happening in semi-public spaces like academic forums and social media. She drafted a memo to NASA leadership recommending accelerated preparation for public acknowledgement of anomalies, if not full disclosure of artificial hypothesis. The memo outlined 3 options: continue silence and risk uncontrolled disclosure through leaks, make a partial announcement acknowledging unusual features while emphasizing ongoing investigation, or make a full disclosure presenting the artificial hypothesis along with caveats about uncertainty. Each option carried risks. Continued silence risked credibility damage when truth eventually emerged. Partial announcement risked appearing to hide information. Full disclosure risked causing panic or looking foolish if mundane explanations somehow materialized later. The choice wasn't hers to make alone. It required coordination across agencies, consultation with international partners, and ultimately political decisions about how humanity should respond to the first potential evidence of extraterrestrial technology. While those discussions continued in classified channels, 3i Atlas kept moving. 400 million kilometers from Earth now, beyond the orbit of Mars, its brightness fading as distance increased but still detectable to modern instruments. Still pulsing every 6.2 hours. Still reflecting light from those geometric panels with efficiency that natural surfaces didn't possess. Dr. Marcus Webb, in his final observation session of May, tracked the object across his detector field and watched the familiar pulse appear in real-time brightness data. Rise, plateau, fall, baseline, repeat, mechanical, regular. Impossible to dismiss as natural variation once you'd seen it enough times to recognize the pattern's perfection. He thought about what was required to maintain such regularity. Natural rotation alone couldn't do it. The object would need to be perfectly rigid, perfectly balanced, experiencing no torques from outgassing or solar radiation pressure that might alter spin rate even slightly, or it would need active stabilization, gyroscopes, reaction wheels, systems that corrected rotation to maintain precise timing. Natural objects don't carry gyroscopes, they don't correct their rotation, they tumble chaotically, their spin rates changing as mass shifts and external forces act on them. But some objects do carry gyroscopes. Objects that were built rather than accreted. Objects designed to maintain orientation, to point instruments in specific directions, to keep solar panels facing the sun, or communication dishes pointing toward destinations. Webb closed his observation session and shut down the telescope. Morning was approaching and chilly. The sun would soon wash out any view of the stars and the faint visitor moving among them. He walked outside into pre-dawn darkness and looked up at the sky, thinking about the fact that somewhere overhead, currently below the horizon from his location, but visible from other parts of Earth, an object was traveling that shouldn't exist according to everything astronomy taught about natural processes. The silence protocol might buy time. It might allow careful analysis and coordinated response. But it couldn't change what the data showed. It couldn't make those geometric panels natural. It couldn't explain away the pulse or the thermal regulation or the systematic ways 3i Atlas violated expectations. Eventually, the silence would break. And when it did, humanity would have to confront a question it had been asking for thousands of years but had never seriously expected to answer. Are we alone? The data was already providing that answer. The silence was just postponing the moment when everyone else would hear it. There's a moment in every profound realization when understanding shifts from intellectual acknowledgement to visceral comprehension. You can know something is true in an abstract sense, can follow the logic and accept the conclusion, but still not feel its full weight. Then something clicks. Some final piece of evidence or some quiet moment of reflection, and suddenly the knowledge moves from your mind to your gut. The implications become real, personal, inescapable. For Dr. Sarah Chen, that moment arrived on June 3, 2025, at 2:30 in the morning, sitting alone in the Mauna Kea control room with a thermal imaging dataset displayed across 3 monitors. She had been analyzing temperature variations on 3i Atlas's surface, tracking how heat distribution changed as the object rotated and as it moved farther from the sun. The work was technical, methodical, the kind of detailed examination that fills research hours with careful measurement and calculation. Objects cool predictably as they recede from a heat source. Solar distance increases, radiant flux decreases, surface temperatures drop according to well-established thermodynamic equations. 3i Atlas was maintaining temperature, not perfectly, not completely, but far better than any passive object should. At its current distance of 430 million kilometers from the Sun, temperatures should have dropped to approximately negative 140 degrees Celsius. Instead, the object was measuring negative 105, 35 degrees warmer than physics predicted for a body simply radiating accumulated heat into space. That excess wasn't decreasing as distance increased. If anything, it was becoming more pronounced. The object was actively regulating temperature, maintaining thermal equilibrium that required internal energy production, not the brief warmth of chemical reactions or residual heat from perihelion passage, sustained controlled energy release that had been constant for weeks as the object traveled outward. Chen stared at the temperature graph, watching the measured values hold steady while the predicted curve declined steadily toward background temperature. The gap between prediction and observation grew wider each day. By the time 3i Atlas reached Jupiter's orbit in late 2025, that gap would be enormous, representing energy output that no natural process could sustain. Something inside was powered, operating, functioning with purpose. She had known this intellectually for weeks. The data had pointed toward it. The classified assessments had stated it clearly. But sitting there at 2:30 a.m., watching temperature readings that shouldn't exist, she felt the knowledge shift from abstract fact to concrete reality. They were observing a machine, not a comet that happened to have unusual features. A constructed object that crossed interstellar space carrying systems that still worked after however long that journey had taken. Systems that activated or intensified after perihelion passage. Systems that maintained themselves, regulated temperature, managed energy, pulsed with mechanical rhythm. And if those systems were active now, then something might be active inside them. Something that made decisions or followed programming. Something that might be aware, in whatever way artificial systems could be aware, that it had passed through a planetary system containing technological civilization. Chen picked up her phone and called Dr. James Morrison despite the time difference. He answered immediately, voice alert. People in this situation didn't sleep regular hours anymore. The thermal data isn't ambiguous, she said. It's not residual heat. It's not chemical reactions. Something is generating power inside that object and has been consistently since we've been able to measure it. I know, Morrison replied quietly. I ran the same analysis yesterday. The energy budget doesn't close without active generation. So we're certain. As certain as we can be without visiting it directly and looking inside. Silence stretched between them. Then Chen asked the question that had been building in her mind for days. If it's powered, if it's maintaining systems, what's it doing? Just existing, or is it recording? Observing? Transmitting? We don't know. The pulse could be incidental, just a byproduct of rotation and reflective panels, or it could be deliberate communication. The thermal regulation could be automatic preservation systems, or it could be supporting active instruments. Without knowing the design, we can't determine function. But it came from another star system. It passed through ours. If it's artificial, if something made it, then it was sent here. Nothing crosses that distance by accident. Morrison was quiet for a long moment. No, he agreed finally. Nothing crosses that distance by accident. That conversation, repeated in various forms across multiple time zones and institutions, marked the beginning of what participants later called the perception shift. The transition from treating 3i Atlas as an astronomical anomaly, requiring explanation, to recognizing it as potential evidence of non-human intelligence. From puzzle to proof. From interesting to existential. The shift happened differently for different people, arriving in different moments triggered by different aspects of the data. For Dr. Marcus Webb, it came while reviewing the geometric precision of the reflective panels and recognizing that their placement maximized visibility from Earth's position during the object's passage. For Dr. Yuki Tanaka, it arrived when she calculated that the 6.2-hour pulse period was suspiciously close to being a simple integer ratio with Earth's rotation period. For Dr. Angela Reeves, it happened during a classified briefing when someone asked, "What would we do differently if we knew for certain it was artificial?" And she realized the honest answer was nothing, because we're already treating it that way. By early June, the researchers closest to the data had largely completed their shift. They spoke carefully in official communications, maintaining scientific caution and appropriate skepticism, but privately they discussed the object in terms that assumed artificial origin, not because they wanted to believe it or because they were abandoning scientific rigor, but because natural explanations had been systematically eliminated and the remaining possibility, however extraordinary, fit the evidence better than any alternative. The implications of that conclusion were staggering and arrived in cascading waves as people thought through consequences. First implication, intelligence exists elsewhere. not theoretical intelligence that might exist somewhere in the galaxy. Actual intelligence that built something that reached our solar system. The ancient question, are we alone, had been answered definitively by an object currently receding past the asteroid belt at 31 kilometers per second. Second implication, that intelligence achieved interstellar travel, not through crude missions that would require life support and impossible energy, but through probes. Artificial emissaries that could survive transit times potentially measured in hundreds of thousands or millions of years. The engineering sophistication implied by 3I Atlas's continued function was extraordinary. Human spacecraft struggled to operate for decades. This object had apparently functioned across timescales that dwarfed human civilization. Third implication, Earth was either the target or happened to lie along a route something chose. The object's trajectory, when traced backward through the galaxy, pointed toward a region containing several interesting stellar systems but no obvious candidate for origin. It could have been traveling for so long that its source star had moved, significantly due to galactic rotation, or it could have been launched from somewhere unknown. Either way, it had entered our solar system, passed perihelion, and was now leaving carrying whatever observations or data it had gathered. Fourth implication, the one that generated the most quiet anxiety in private discussions. If this probe came, others might follow. 3I Atlas might be one of many scattered throughout the galaxy, a network of observers mapping planetary systems, cataloging worlds, identifying places of interest. Human civilization had only recently become detectable at interstellar distances through radio emissions and atmospheric chemistry changes. Something might have noticed and dispatched an observer, or this probe might have been traveling for eons and happened to pass through at the moment humanity had developed tools sophisticated enough to recognize it as artificial. The timing bothered many researchers. Why was 3I Atlas discovered now in 2025 when observational astronomy had reached unprecedented sophistication? Had similar objects passed through centuries earlier when humans lacked instruments to detect them? The probabilities suggested that interstellar probes, if they existed at all, should be rare enough that encountering one during humanity's brief technological age was unlikely, unless the probes were numerous, part of an extensive survey project, or unless they were specifically attracted to systems showing signs of technological development. Dr. Helen Mora at ESO spent a disturbing afternoon in early June calculating detection probabilities under different assumptions. If interstellar probes visited randomly, the chance of detecting one during humanity's century of advanced astronomy was roughly 1 in 10,000. But if probes specifically targeted systems with detectable technosignatures, radio emissions, atmospheric pollution, artificial light visible from space, then the probability rose dramatically. Under that model, detection was almost certain within decades of a civilization becoming space-capable. She didn't publish that analysis. It was too speculative, built on too many unknowns. But she shared it with several colleagues who found the logic uncomfortably sound. If 3I Atlas was here because humanity had become detectable, then Earth had been noticed, cataloged, perhaps even evaluated. The question of whether the object was still observing generated intense discussion. Its perihelion passage had brought it within 97 million kilometers of Earth at closest approach, close enough that any instruments aboard would have had clear views of our planet. If it carried telescopes with resolution comparable to humanity's best instruments, it could have resolved continental features, perhaps even individual cities. If it carried spectroscopic equipment, it could have analyzed Earth's atmosphere and detected oxygen, methane, industrial pollutants, the chemical signatures of biological activity, and technological civilization. What it would have seen was a planet covered with electromagnetic emissions, radio, television, radar, the constant chatter of a civilization that had spent the last century screaming its presence into space without considering who might be listening. If 3I Atlas was a probe, if it was gathering data, then it had collected comprehensive evidence of humanity's existence, capabilities, and characteristics. And now it was leaving, carrying that evidence, potentially transmitting it, though no signals had been detected, heading back into interstellar space where, eventually, it might return to whoever sent it or upload its findings to some network of similar probes or simply continue traveling, a lone emissary bearing humanity's first portrait taken by external observers. Dr. James Morrison presented these implications to a classified briefing on June 5th, attended by representatives from NASA, the Department of Defense, and the intelligence community. His presentation was titled Strategic Implications of Potential Non-Human Intelligence Contact, and it treated the scenario not as speculation, but as the most probable interpretation of available evidence. We need to consider what happens next, Morrison told the assembled group. If 3I Atlas is artificial, and if it observed Earth during passage, then we exist in a fundamentally different universe than we existed in last July. We are known, we are cataloged, and we have no information about who is doing the cataloging or what their intentions might be. Could it be hostile? Someone asked. We have no basis for evaluating intention. The object showed no aggressive behavior, didn't alter course toward Earth, didn't attempt communication we could detect. It simply observed if our interpretation is correct and continued on its trajectory. But something could follow, something less passive. That's possible, Morrison acknowledged, but we should be careful about projecting human frameworks onto non-human intelligence. Concepts like hostility or cooperation might not apply. The probe's purpose could be purely observational, or it could be performing functions we can't imagine because we lack the context to understand the goals of beings with different evolutionary history and technological development. What's your recommendation? Short term, continue observation while the object remains visible. Document everything. Collect maximum data. The object will fade beyond detection capability sometime in late 2025 based on current brightness trends. After that, we'll have lost our only direct source of information about whatever civilization created it. Medium term, prepare for the possibility of additional visits. If 3i Atlas was part of a survey program, other probes might pass through the solar system in coming years or decades. We should establish protocols for detection, observation, and potentially interaction if an object shows interest in communicating. Long term, recognize that humanity may have entered a different phase of cosmic existence. If we've been observed, if information about Earth has been collected, then we're potentially part of something larger than ourselves. Whether that's beneficial or neutral or concerning depends on factors we can't currently assess. The briefing continued for 3 hours, covering scenarios ranging from mundane to catastrophic. What if the object had been dormant for millions of years and activated by chance when passing through our system? What if it had been sent recently from a nearby star, implying active civilizations within tens of light years? What if its thermal signature indicated some power source humanity didn't understand, possibly representing physics beyond current knowledge? Every question generated more questions. Every answer revealed new uncertainties. The only certainty was that the universe had changed, or rather humanity's understanding of its place in that universe had changed, and there was no returning to the comfortable assumption that we were alone. By mid-June, the silence protocol was becoming unsustainable. Too many researchers had reached the same conclusion independently. Too many observations had been made by too many facilities. Amateur astronomers continued tracking 3i Atlas and posting findings online. Discussion forums filled with speculation about why professional astronomers seemed reluctant to discuss the object's unusual properties in detail. Dr. Sarah Chen received emails almost daily from colleagues asking pointed questions about the thermal data, the pulse mechanism, the geometric features. She answered carefully, confirming observations without stating conclusions, but her caution itself communicated something. Scientists are usually eager to discuss interesting findings. Reticence suggested sensitivity, and sensitivity suggested the findings were more significant than public statements acknowledged. On June 12th, a graduate student in Germany named Klaus Hoffmann posted a detailed technical analysis to Archive, the preprint server where researchers share papers before journal publication. The paper was titled Anomalous Properties of Interstellar Object 3i Atlas, Evidence for Non-Standard Composition or Structure. It compiled publicly available observations, noted the systematic ways the object defied conventional cometary behavior, and concluded that either humanity's understanding of cometary physics needed substantial revision or 3i Atlas represented something categorically different from natural solar system objects. The paper didn't explicitly state artificial, but it ruled out most natural explanations, and noted that the object's properties might warrant consideration of origins or modifications not typically encountered in planetary system formation scenarios. That careful academic language translated plainly enough for anyone reading closely. This might not be natural. The paper was downloaded 20,000 times in its first 48 hours. Science journalists began covering it. Articles appeared asking why such unusual findings hadn't been more widely publicized. Questions were directed at NASA and ESO about whether official analyses had reached similar conclusions. The organizations issued careful statements acknowledging that 3i Atlas showed interesting characteristics that deserved continued study. They confirmed observations matched what independent researchers were reporting. They emphasized that scientific analysis required time and thoroughness before reaching definitive conclusions. What they didn't say, but what the careful phrasing implied to attentive readers, was that those conclusions, once reached, would be significant. You don't exercise this much caution around ordinary comets. You don't restrict information flow unless the information matters. Dr. Angela Reeves watched the media coverage spread and knew managed disclosure was no longer possible. The community had been too large, the data too widely distributed, the implications too obvious once people looked carefully. By late June, someone would make the explicit claim that 3i Atlas was artificial. That claim would generate enormous attention, and NASA would face the choice of confirming, denying, or equivocating. She drafted a memo recommending controlled acknowledgement. Confirm the anomalies, present them factually, acknowledge that artificial origin was one hypothesis under consideration, emphasize uncertainty and ongoing investigation. Don't overstate, don't dramatize, but don't deny what the data showed. That memo reached senior leadership on June 15th. The response came back on June 17th. Prepare a formal statement for release within 2 weeks. Coordinate with international partners. Brief congressional leadership. Develop communication strategy for multiple scenarios depending on public reaction. The silence protocol was ending. Not with dramatic announcement, but with careful, controlled acknowledgement that something unusual had been observed and that its nature remained under investigation. Dr. Marcus Webb, finishing his final observation session of 3I Atlas before the object faded below his telescope's detection threshold, watched the familiar pulse appear one last time. 6.2 hours. Rise. Plateau. Fall. Baseline. The pattern that had repeated several hundred times since perihelion without variation. He thought about the possibility that somewhere, encoded in systems humanity couldn't see, information about Earth was being stored or transmitted. Images of our planet. Spectroscopic data about our atmosphere. Perhaps even intercepted radio signals, decades of human broadcasts inadvertently beamed into space, now captured by equipment designed for exactly that purpose. If 3I Atlas was artificial, if it was observing, then humanity had been seen. Not as we imagined ourselves, but as we actually were. A technological species confined to a single planet, throwing energy and pollution into space with abandon, recently emerged from ignorance about the cosmos, still learning to use the tools that allowed us to recognize visitors from beyond. What would that data say about us? What conclusions would be drawn by whatever intelligence eventually accessed it? Webb closed his observation session as morning light began washing out the stars. 3I Atlas was still out there, still traveling, still pulsing, but beyond his ability to detect anymore. Larger telescopes would track it for a few more months, then it would fade completely, disappearing into darkness, carrying whatever it carried back toward the space between stars, leaving behind humanity, altered by the encounter whether we fully understood it yet or not. We had seen something we couldn't explain naturally. We had documented it carefully, analyzed it thoroughly, and reached a conclusion that defied comfortable assumptions. The perception shift was complete for those closest to the data. It was beginning for the wider scientific community. Soon it would reach the general public, arriving not as definitive proof, but as unsettling possibility, as the recognition that the universe might contain others, and that some of them might have noticed us. What happened next depended on how humanity processed that knowledge, and what other visitors might be traveling through darkness toward encounters we couldn't yet predict. June fades into silence. Not the comfortable silence of questions answered, but the heavy silence of people who have seen something they cannot unsee, and must now decide how to live with that knowledge. 3U Atlas continues outbound at 31 kilometers per second, receding past the asteroid belt toward the orbit of Jupiter. Distance dulls its brightness. Each night it appears fainter in telescopes, harder to detect against the background stars. By late June it measures magnitude 21, visible only to sophisticated instruments with long exposure times. Predictions suggest it will fade below detection threshold for most facilities by September 2025. After that, only the most powerful telescopes on Earth and in space will track it, and only for a few additional months before it vanishes completely into darkness, another dim speck among billions indistinguishable, except by trajectory and the knowledge of what it might represent. The pulse continues, every 6.2 hours without deviation. Every measurement confirms the same pattern, the same amplitude, the same achromatic behavior across all wavelengths. Something inside maintains timing with precision that suggests mechanisms still functioning, systems still active, purpose still being fulfilled even as the object travels away from the sun and back toward interstellar cold. Dr. Sarah Chen conducts her final observation on June 28th, watching the familiar brightening appear in her detector one last time before the object drops below Mauna Kea's visibility threshold. She records the last phone. Data with the same careful methodology she has used for 6 months, measuring brightness to 3 decimal places, noting timing to the nearest second. The numbers go into files that have grown enormous with accumulated observations. Thousands of data points, hundreds of hours of telescope time, all documenting something that should not exist according to every model of natural cometary behavior. She files her report through the usual encrypted channels, confirms the pulse persists, notes the thermal signature remains elevated above predictions, adds no interpretation because the interpretation is already understood by everyone who reads these reports. The object is what it appears to be. Analysis has been exhausted. Natural explanations have been eliminated. What remains is simply continuation. Continued observation until the object fades beyond reach. Continued documentation of behavior that maintains its impossible regularity. Continued waiting for something to change, or for clarity to emerge, or for whatever comes next. Across the world, other observers conduct similar final sessions as 3I Atlas moves beyond the range of their instruments. Each contributes data to the collective record. Each adds confirmation that the anomalies persist, that nothing has normalized, that the object departs as strange as it arrived. NASA's official statement releases on July 2nd, 2025, timed deliberately for the slow news cycle following the mid-year break when attention spans are fragmented and shocking announcements get diluted by distraction. The statement is brief, technical, carefully worded. Interstellar Object 3I Atlas continues to display physical and behavioral characteristics that differ from typical cometary bodies observed in our solar system. Ongoing analysis suggests the object's composition, thermal properties, and brightness variations warrant continued study. Multiple explanations remain under investigation, including unusual material composition, non-standard internal structure, and origins in stellar environments significantly different from our Sun. Observations will continue while the object remains detectable. The word artificial appears nowhere in the statement. Neither does probe or intelligence or technology. But the phrasing, non-standard internal structure, continued study, multiple explanations under investigation, communicates enough to those who know how to read institutional caution. This is not a routine announcement about a typical interstellar visitor. This is acknowledgement that something unexpected has been encountered and that its nature remains unresolved. Media coverage follows predictably. Science journalists write articles noting the unusual properties. Astronomy forums fill with speculation. A few researchers speaking anonymously suggest the object's characteristics might indicate artificial origin, though they emphasize no definitive conclusion has been reached. The story generates attention for several days, then fades as other news cycles dominate. Public interest remains but doesn't reach the level of cultural phenomenon or widespread concern. Most people file it mentally under interesting space news and move on with their lives. Those who cannot move on are the researchers who have spent months with the data, who have run the calculations, who have eliminated the natural explanations one by one and confronted what remains. For them, July 2025 marks not resolution but continuation of a strange liminal state. They know what they have almost certainly observed. They cannot yet say it definitively, and so they wait. Wait for the object to reveal something more explicit, some undeniable signature of artificiality that would remove all doubt. Wait for better analysis methods or new data that might provide the natural explanation everyone secretly hopes for, because natural would restore comfortable assumptions. Wait for something else to appear. Another visitor, another object showing similar properties. Confirmation that 3I Atlas is not unique but part of a pattern. The waiting extends into the long months that follow. Telescopes continue tracking the fading speck of light, recording data that shows nothing changing. Same pulse, same thermal excess, same geometric reflectivity panels visible in high-resolution imaging. The object behaves exactly as it has behaved, following trajectory and rotation and energy output patterns that suggest systems maintaining themselves with mechanical precision. Dr. James Morrison assembles the final comprehensive report in August 2025, a document summarizing 6 months of international observation and analysis. The report runs to 137 pages, including appendices, graphs, spectroscopic data, thermal models, and comparative analysis with every known cometary nucleus. Its conclusion, stated with appropriate scientific caution but unmistakable implication, notes that 3I Atlas displays characteristics inconsistent with current understanding of natural small body formation and evolution, and that further observations of similar objects would be valuable in determining whether this represents an anomalous outlier or indicates phenomena not yet incorporated into planetary science models. The report circulates through classified channels and selected academic institutions. It is not published publicly. It is not released to media. It exists as internal documentation, establishing the evidentiary record for whatever discussions or decisions might follow once the nature of 3I Atlas becomes undeniable or once similar objects appear to confirm the pattern. By September 2025, most telescopes have lost the signal. The object has faded below magnitude 23, detectable only as a faint point requiring hours of exposure time and sophisticated image processing. The James Webb Space Telescope conducts final observations in mid-September, capturing infrared data showing the thermal excess persisting. Despite the object now being beyond Saturn's orbit, where solar heating is negligible, that observation eliminates the last remaining possibility that residual heat from perihelion was responsible. Something inside is generating power. Something inside is active. The pulse is confirmed in those final observations. 6.2 hours. Still precise. Still regular. Still broadcasting or simply existing with timing that natural objects do not maintain. Then 3I Atlas fades completely. The last confirmed detection occurs on September 28, 2025. After that, the object is too faint, too distant, too small against the immense darkness of space beyond the planets. It continues traveling, of course, following its hyperbolic trajectory out of the solar system and back into the interstellar medium, but humanity can no longer see it, can no longer track it, can only know it exists somewhere in the dark, moving at 31 kilometers per second toward a destination unknown, carrying whatever observations or data it gathered during its passage through our neighborhood. Dr. Sarah Chen returns to routine work in October, observing asteroids and comets that behave as comets should behave. But sometimes late at night, when the observatory is quiet and the stars are sharp against the dark, she thinks about the object still traveling out there beyond detection. Still pulsing, probably, though no one can confirm it anymore. Still maintaining systems that should not function after millions of years in space. Still carrying information about Earth, if the artificial hypothesis is correct. And she wonders who will eventually receive that information, and how long it will take to reach them, and whether something else is already on its way, having been summoned or notified, or simply following a route that brings it through our system in years or decades or centuries hence. The universe feels different now, larger and more populated, but also more uncertain. The comfortable assumption of isolation has been challenged. The data exists. The observations cannot be erased. Whatever 3i Atlas was, it passed through and was documented and left behind questions that have no answers yet and may not have answers for a long time. We are observed or we are not. We are alone or we are not. We are cataloged or we are not. The evidence suggests possibilities we cannot confirm and cannot dismiss. And so we wait in the aftermath, watching the sky with instruments that are suddenly inadequate, wondering what else moves through the dark and whether we will recognize it when it arrives. The silence is not empty anymore. It is filled with attention, with the possibility of eyes looking back from across the interstellar distances we always assumed were barriers. 3i Atlas proved those distances can be crossed. Something built it, something sent it, something may be waiting for its return or for its signal or for the right moment to send others. June 2025 will be remembered as the month we stopped being certain we were alone. The month when data forced recognition of possibilities we had only imagined. The month when a visitor from another star left our system carrying information about us while we watched helplessly, unable to intercept or communicate or understand. And now we wait. For clarity. For repetition. For the next visitor. For whatever comes after the first contact we didn't recognize as contact until it was already leaving. The sky continues overhead, vast and dark and full of objects we cannot see. Some are natural, some might not be. And we will never look at that darkness the same way again.